Alright, this is the Chapter 6 study guide, section 6.1 to 6.3. First section is 6.1, differential equations. So to solve these, you have to integrate both sides with respect to t. So come over here, and we're going to integrate this side. Integrate both sides with respect to x, rather. Alright, we integrate this with respect to x, you get y is equal to, pull out the 6 constant, and integrate x to the 5th. We know that if you integrate x to an n power, the integral is x to the n plus 1 over n plus 1. So this is x to the 6th over 6. Those 6's cancel out. Minus, I'm going to factor out this 2. And I recognize that secant squared is the derivative of tangent. So if you integrate secant squared, you get tangent of x. Don't forget your plus c, because you're taking a general solution here, which is basically an antiderivative. So y is equal to x to the 6th minus 2 tangent of x plus c. That is your final answer. Number 2, same thing, except we're going to be able to solve for our plus c because we're given an initial condition. Initial condition means they give you sort of a point on the graph. So we know, like here, we know the slope, which is your derivative, but this kind of gives us, in a sense, a y-intercept of that graph. So we integrate both sides, this time with respect to t, only because our variable changed to t. So integrate the left side, you get y, the original function. Integrate 6 with respect to t, you get 6t minus, let's factor out this 7 constant in front of cosine. Alright, the antiderivative of cosine is sine of t, and it's plus c, but then we plug in our initial conditions after we take that derivative. So y is equal to 6 when x is equal to 0. On your guide, I accidentally swapped those. So this is y of 0 equals 6. The 0 should be the x, and the 6 should be the y. So we plug in 6 for y, and everywhere you see a t, everywhere you see a t, you should put 0. So 6 times 0 minus 7 sine of 0 plus c. So that 6 is equal to 0 minus sine of 0 is 0 plus c. So 6 is equal to c, and you just plug this back into this equation right here. So y is equal to 6t minus 7 sine of t plus 6, because 6 is c. Number 3, you're finding an indefinite integral. It's just basically an antiderivative. So it's sort of like a general solution here. So this is kind of stuff from chapter 5. It might seem like you have to use some sort of quotient rule, but all you have to do is separate the fractions. So integrate x cubed over x squared plus 1 over x squared. So that we know is, you simplify this into x, and this is plus x to the negative 2 power. For x, for both of these, use the power rule. The integral of x to the n is equal to x to the n plus 1 over n plus 1 with respect to x. So integrate this, you get x squared over 2, the first one, and when we integrate this, we get, let's see, x to the negative 2 plus 1 over negative 2 plus 1. So that's x to the negative 1 divided by negative 1, which is negative x to the negative 1. So this is minus 1 over x. Don't forget your plus c, because we're taking an indefinite integral, meaning we don't have the a and the b here. All right, here again, indefinite integral is the same thing. So you change this into 1 over z squared plus 1 over z to the 6th plus z squared over z to the 6th. So 1 over z to the 6th is z to the negative 6. And this is going to be 1 over z to the 4th, so it's z to the negative 4th. And again, you use power rule. So z to the negative 6 plus 1 over over negative 6 plus 1. Be careful with your negative signs here. So that's z to the negative 5 over negative 5 plus z to the negative 3 over negative 3. And it would be, you want to get rid of your negative exponent, so it's 1 over, it's negative 1/5, and you have z to the 5th in the bottom, and then minus 1 over 3z to the 3rd. That's your final answer. Don't forget your plus c. All right, number 5. We're going to have to use integration by substitution here. This is section 6.2. So we have a composition function. It's sort of like chain rule. You let your inside function be u. Then we're going to have to take the du, the differential or derivative, So the derivative of 8x is 8, and you have to stick in your dx. And the reason is because du with respect to x is equal to 8. But we want to solve for du because we want to plug that into the equation, and you can multiply the dx by both sides, so du is 8 dx. So in this function, since we said u is 8x, we're taking the integral of cosine of u. Alright, so we don't find a dx in here, so we can't substitute this dx for anything yet unless we divide by 8 on both sides. So now we have dx is equal to du over 8. Factor that constant out, that's really a 1/8 integral of cosine of u with respect to u. We know that sine has a derivative of cosine, so this is 1/2 sine of u. And once you're done integrating, you put your u back into your function. So this is really 1/2 sine of 8x. Don't forget your plus c. Really, this plus c is right here, but I'm lazy. I don't tack it on to the end. Number 6. Okay, here again, you actually don't use integration by parts. You might think, oh, well, hey, this is a product. You're going to use integration by substitution. The way you can tell is anytime you see a function, the inside function and his derivative also occurs in there, that's when you use substitution. So let u equal to x to the third power. That means du is equal to, let's see, we're going to take the derivative here. So du is equal to 3x squared, and then tack on your dx. So we change this into, all right, I'm going to reorder this just so you can see what we're doing here. X, sine of x cubed. I'm going to tack on this x squared after, then tack on my dx. All I did was change the order here. So it's the integral of sine of, we replaced x cubed with u. All right, now I see an x squared dx, and I have an x squared dx right here, but I want to get that 3 away from it. I want to solve for x squared dx. So x squared dx now, once I cancel these out, is equal to du divided by 3. So I'll put this du divided by 3 here. All right, once I put that in, I can factor out the 1/3. All right, 1/3 integral of sine of u, and then you just have to remember who has a derivative of sine. It's negative cosine has a derivative of sine. Okay, so it's 1/3 times negative cosine of u, and let's go ahead and bring that negative in front. Negative 1/3 cosine of, and replace the u again with x cubed. Put that back in. Don't forget, it's an indefinite integral plus c. Always a plus c. There's some arbitrary constant there. All right, again, antiderivative. We're going to do integration by substitution again. This time, our inside function is actually sine, okay? So if you want to look at this, I'm going to type it in. I'm going to write it down the way you would have it in your TI-84 calculators. So this is 2 sine of x squared. That's what the sine squared of x is. It's sine of x, and you square the whole thing. All right, times cosine of x dx. Again, the reason I know I'm doing substitution and not integration by parts is because my inside function, his derivative is also in there. So I'm going to let u be equal to sine of x, and then du is going to be equal to cosine of x dx. So that's going to be mighty convenient. If you integrate this, rewrite this, remember sine of x, we said it's going to be u. All right, but it was sine x squared, so we're going to do u squared. And then cosine of x dx is du. So replace this cosine of x dx with du. Now we just have a regular power function. So this is, we can pull that 2 out. So we take the integral of u squared with respect to u, and then we just use our standard increase the exponent rule. So we do 2 times, this is 2 times u cubed over 3. All right, and that's going to be equal to, I'm just going to pull this out, this 2/3 out in front, and then replace the u cubed with, I remember u is sine of x, so replace the u with sine of x, so instead of u cubed, it's sine of x cubed. Don't forget your plus c, because it's an indefinite integral. All right, move on to number 8. Now we're going to use integration by parts. This is section 6.3. So the rule is the integral of u dv is equal to u times v minus the integral of v with respect to u. So always call the function that can kind of collapse into an easier function, always call that one u, and then everything else is dv. So we're choosing a nice well-behaved u, everything else is dv. So u is going to be equal to x, and du is going to be equal to 1 dx because the derivative of x is 1. Now, a little different than I did it in class. I'm going to put my dv up here, and then I'm going to put my v down below. All right, so dv is everything else. dv is sine of 2x with respect to x. And to find our original v, we have to integrate this. Now we know that the integration, we know that sine is a derivative of negative cosine. So we do negative cosine of 2x. But to compensate for this 2 here, and what you're going to have is, if you take chain rule, don't forget you're multiplying the inside function. The integral is actually negative 2 cosine 2 dx. And just to confirm that really quick, if you take the derivative of negative 2, actually it'll be negative 1/2 to compensate for that 2. If you take the derivative of negative 2 cosine of 2x, if you notice, all right, first thing we do, if you take the derivative of negative cosine, you get sine of 2x. And then you take the derivative of the inside function. So we have to put the 2 out in front. But we can see this 2 sine of x, this doesn't have a 2 sine of x. So that 1/2 here is basically to cancel out that 2. So you can see how that works. So our v is negative 1/2 cosine of 2x. So we put in our little equation. We do this integral of u dv is equal to u times v minus integral v with respect to u. U is x. V is negative 1/2 cosine of 2x. All right, and then minus the integral of, taking the integral of negative 1/2 cosine of 2x. And then du is actually just dx, which is convenient. So simplify this. This is negative 1/2 x times cosine of 2x minus, all right, I'm going to pull this negative 1/2 out, so that's going to end up being a plus 1/2 here because you have a negative and a negative. And the integral of cosine 2x is just sine of 2x, but again, to compensate for that 2 there, it's actually 1/2 sine of x. So it's negative 1/2 x cosine of 2x, bringing this thing, plus 1/4 sine of 2x. Don't forget your plus c, because again, we're taking an indefinite. All right, number 9. We're going to use integration by parts again. Again, you want to make your nice, well-behaved function your u, okay? You don't want to make this e function u. So this is our u right here. Everything else is going to be our dv. So u is equal to 6t, and our dv is equal to e to the 5t dt. All right, so we got to take our du because we're going to need that. So du is a 6 dt because the derivative here is 6, and we have to integrate this thing to get v. Now we know that e to the t is its own derivative, but again, because you have that constant 5 here, and you got to factor in like what chain rule does to that, you have to put that 1/5, just like in the other one we have to put that 1/2 to compensate for chain rule. So the integral of that is 1 to the 5th e 1/5 e to the 5t. So again, it's u times v minus integral v with respect to u. So we're going to do u is going to be 6t. V is going to be 1/5 e to the 5t. All right, and then we do minus. We integrate 1 to the 5th e to the 5t. And du is just 6 dt. All right, combine these constants right here. We got 6/5 t e to the 5t. All right, pull these constants out. I'm going to pull this 1/5 out and this 6 out, so it's going to be minus 6/5. And again, we already integrated e to the 5t. We integrated e to the 5t right here, which is 1/5 e to the 5t. And we just combine those constants there by multiplying. So this is 6/5 t e to the 5t minus 6 over 25 e to the 5t. It's an indefinite integral. Don't forget your plus c. All right, so we're going to move on to number 10. And this one is going to be a all right, number 10 is potential bonus material. All right, so if you're having trouble with this, don't worry too much about it. At least begin to attempt it to get partial credit on it. But this is a very challenging problem. But we're going to kind of make it a little easier here. So we're going to have to use chain rule twice. The reason being because on the other one we had just a t power. Here we have the variable squared power. So this thing eventually will collapse. When you keep taking the derivative, it'll collapse to nothing. So we're going to make that our u, and we're going to make everything else our dv. So we use the standard procedure that the integral of u dv is equal to u times v minus integral v du. But I'm going to use a little trick here. I'm going to use a table of integrals trick. This is called tabular integration. You can see how this is worked out on page 344 and 345. So on page 344 and 345, and this is just a little shortcut for when you have to do integration by parts repeated amount of times. So I'm going to write my u is equal to 3 theta squared. That makes my du to be it's going to be 6 theta. Now I know that this is going to be end up being used again. So if I take the derivative, this is the second derivative of u. It's actually going to be just 6. So it's 6 theta d theta, whatever. And then this is going to end up being 6 d theta. All right, and if I make my dv equal to everything that was left here, so sine of 1/2 of theta d theta, that means my v, or if you want my first integral, if I integrate it one time, what I'm going to have is I'm going to have negative cosine of 1/2 theta. And just like we did before, to compensate for that 1/2, I'm going to have to actually it's going to be negative 2 cosine. You have to multiply by 2. And if I take that integral again, because I will end up having to do it again, and if I don't pull out my constants, what we have is you have to compensate for it again, so it's negative 4. The integral of negative cosine is negative sine. So we have negative 4 sine of 1/2 theta right there. All right, and then we're probably going to have to take it one more time, the integral. If you take the integral the third time, you actually won't have to if you factor out the constant. But I'm going to do this just to show you a little shortcut. This is equal to, and we're going to have, think, negative 8 sine of 1/2 of theta, because the integral of sine is going to be, the integral of sine is actually negative cosine again, so what you have is a little mistake here. So it's negative 8 times negative cosine, if you just treat this as like the positive sign and worry about your constant later. So we have negative 8 times negative cosine, so just make that positive 8 times cosine here. Alright, so this is our original dv. Then if you integrate it once, you get this. Integrate it twice, you get this. Integrate it a third time, you get this. And if you notice, we're always doing u times v minus some integral here. So we're doing u times v. So I'm going to denote that by this little thing right here. Alright, so you're doing u times v, which in this case is 3 theta squared. So 3 theta squared minus our v is, times. So it's 3 times v. So times negative 2 cosine of 1/2 of theta. And then it's minus this integral. But this integral, the v du here, if you look at the v du, that's it's going to be another product, okay? So what I'm going to do to take a little shortcut here is I know I'm going to have to integrate again. So I'm going to do the integration again, which is going to do this u times this v. But since there's already a minus and you got to subtract again, so I have that minus here. It's going to be minus 6 theta times negative 4 sine of 1/2 theta. And what I do is I'm going to keep going until this collapses to 0 essentially. So I know I'm going to have to do it again here, but this time it's going to be minus minus, so it's going to be plus this integral right here, okay? So we'll go over that in case it's confusing anyway. All right, so we're end up having to do it a third time here. So what we're going to end up doing is multiplying this du effectively, this du times this v. So when we do it again, but it's kind of minus minus, so this time it's going to be plus this thing, plus 48, and that's 48 cosine of 1/2 of theta. The way I got the 48 was the 6 and the 4 here. And if you notice, if we did do it one more time like that, if you take the third derivative here, the derivative of 6 is just 0. So it doesn't matter what this integral is, this fourth integral is, you don't have to take it. Because the fourth integral, it's being multiplied times 0 here. So you're not going to be, it would be minus 0 effectively. So you're not going to have to compensate for that. So this is a shortcut to do integration by parts several times. We simplify the terms here. So this is -6, because I multiplied the 2 and the -2 and the 3. -6 theta squared cosine of 1/2 of theta minus, all right, I got a -6. It's really -6 times -4, so it's really plus 24 sine of 1/2 of theta, and then it's plus 48 cosine of 1/2 of theta. And, you know, plus c, that would be our indefinite integral, but don't forget, this is a definite integral problem. So instead of having a plus c, what we're going to do is we're going to take this whole problem right here. All right, we're going to evaluate it at pi, and then we're going to subtract from that it evaluated at 0. So don't put it into your calculator. I'll show you actually how to cheat a little bit. You can just throw this into your calculator, but it actually takes more time to throw it in. So just evaluate this at pi. So we've got -6 theta squared, or -6 pi squared, and I'll show you why it's okay that I made the mistake there, times cosine of, now this is 1/2 of pi. Cosine of pi over 2, we happen to know that that's 0, so this term's going to go away, plus 24 sine of 1/2 of pi, so it's sine of pi over 2. Alright, and then plus 48 cosine of 1/2 of, this is going to be pi right here, okay? Alright, that thing, so we got that covered right there. So that's it, evaluated at the upper integral, and then we subtract it from this evaluated at the lower one, 0. So, or not subtracted from, we subtract from it this, so we subtract from that -6, 0 squared times cosine of, you know, 1/2 times 0, but that's going to collapse to 0 again, plus 24 sine of 0, which that's 0, plus, all right, 48 cosine of 0 over 2, you know, 1/2 of 0. And here's the thing, this collapses to 0 because cosine of pi over 2 is 0. This collapses to 0 again. This collapses to 0 because it's 0 times something. This collapses to 0 because sine of 0 is 0. So all this is really, it's 24 times sine of pi over 2. Sine of pi over 2 is 1, so it's 24 times 1 minus, oh, I forgot one little thing here. So I made one little mistake. It's actually, if you do your integral properly here, it should be 24 theta right here. This 6 times 4 here, I forgot that theta. I kind of left that off. So this is 24 pi right there. And like that's 24 times 0, which it doesn't matter. Alright, and so this should be 24 pi times 1 here. So let me erase this here. 24 pi, because sine of pi over 2 is 1. And then this is, don't forget this minus way in the front here. So it's minus 48 times, this is 48 times cosine of 0 is 1. So your final answer is 24 pi minus 48. There you go. Alright. So now we're going to move on to number 11. Number 11, again, this is actually a slightly challenging integration problem by substitution. So, and it's a definite integral problem, just so we can get more practice with that. It's the integral of 1 over 2. What I'm going to do is I'm going to separate these fractions to make things a little clearer. Alright, that times x plus 1 over 1 times dx. And you're going to use integration by substitution, and you'll see why in a second. Again, always make your furthest inside function the u. Then, so it's x squared plus 2 make that your u, and then our du is going to be, take the derivative here, that's 2x, and then this derivative is plus 2. So take this thing, and then, don't forget your dx. And you might think, well, I don't see a 2x plus 2 in here, but factor out the 2. So factor the 2 out of this thing, 2 times x plus 1 dx, and we have an x plus 1 dx here. So if you divide by 2 on both sides, du divided by 2 is x plus 1 dx, so we can make that substitution. So you have 1 over, remember x squared plus 2x, we said we want that to be u. So it's 1 over u squared times, and this whole thing right here, x plus 1 times dx, is just du divided by 2. Factor out your 1/2 so you don't have to deal with it. So this is the integral, 1/2 times the integral of 1 over u squared. And this is just a negative exponent problem now with respect to u. So if we want to take the integral of u to the negative 2, that's the same thing as u to the negative 2 plus 1 over negative 2 plus 1, which is equal to u to the negative 1 divided by negative 1, which is negative 1 times negative 1 over u. That's what that is. Okay, so this is 1/2 of 1 over u. But don't forget, this isn't just a plus c problem. This is this thing, okay? Evaluate it. You have to do the whole capital F of a, b minus capital F of a. So plug your u back in first. Okay, so we have evaluate between 1 and 2. So when we plug that in, you have 1/2 times 1 over u is x squared plus 2x. Alright, and we're evaluating that at 2 minus that evaluated at 1, so it's 1/2 of 1 over, over 2 squared plus 2 times 2 minus 1/2 times 1 over 1 squared plus 2 times 1. And what you get when you subtract these, you just simplify. You should get negative 1/16 for this one right here, and for this one over here, you should get 5 over 48. And the reason you get the negative 1/16 actually is that there's this negative right here. I kind of left it off here. So this is 1 times negative 1 over u, but you bring your negative in front, so I kind of forgot that here. There's a negative in front. So this is negative 1/16 plus 1/6 right here, and that simplifies to 5 over 48. You could also just throw this into your calculator and do that. Alright, number 12, this is just something we wanted to cover. You can really just throw this into your calculator. So in your calculator, what you do is you should put in your y1 line, you do e to the 2x cosine, open parentheses, 3x, close parentheses, and then you go to your graph. Make sure in your graph you want to set your window to where it at least covers from -1 to 1. And whenever you do graph it, make sure you can see the whole graph from -1 to 1. Nothing's cut off. Then you hit the second button, you hit calc, and you go down to the option where it says 7, and it takes the integral of f of x dx. And when you do that, you should get a decimal, something that looks like 0.859, and then a bunch of other numbers. And if you round that to the nearest 3 decimal places, actually the 9 has like a 7 behind it, so it actually rounds up to 0.860. And you could also check your table to find the exact value, but it's something really complicated. On the page, let's see, I think it's page, page 616 up here, table number 108. So it's really complicated. You can't do this by integration by parts, but somebody really brilliant found out how to do this on the table. And you can see the table looks like this: a to the x of cosine bx dx is equal to e to the ax over a squared plus b squared, open parentheses, a cosine of b, x plus b sine of bx, and that plus c. And all you do is you would plug in the 2 everywhere you see an A, and you would plug in the 3 everywhere you see a B, and that will give you the exact value. But It's a really complicated table, so we're not going to bother using that. We're going to move on to number 13. This is a sort of a basic application for integrals, okay? All we do is we're just the area underneath the curve for 8 sine of x is really just the same thing as the integral from 0, in this case 0 to pi, of 8x sine of x. So what we're going to do is we're going to use integration by parts. Let 8x equal to u, and let sine of x dx equal to dv, so u is equal to 8x, which means du is equal to 8 dx. Alright, dv is equal to sine of x dx, and we know that the integral of sine is negative cosine of x, because negative cosine of x's derivative is positive sine of x. So using integration by parts, you have negative 8x times cosine of x. I took the negative from the cosine, brought it in front. That minus the integral of negative cosine of x, and our du here is just 8 dx, so times 8 dx. So this is negative 8x cosine of x. The integral of negative cosine is just going to be negative sine, so negative sine times this negative 1. So then that's going to be plus sine plus 8 sine of x right there. And we evaluate this between, so this is our integral. It has a plus c technically, but since we're really taking a definite integral, you evaluate this thing between 0 and pi. So we just evaluated at pi, so this is negative 8 pi times cosine of pi, and we know that cosine of pi is negative 1, plus, we can do plus 8 sine of pi, but sine of pi is 0, and then that minus, we have minus 8 times 0, because x is 0, cosine of 0, plus 8 sine of 0 right there. Okay, so see, this is the only thing that's not 0. This thing's 0, sine of pi is 0, sine of 0 is 0. So it's just negative 8 cosine, negative 8 times negative 1, negative 8 pi times negative 1. So your answer is negative 8 pi right there. Alright, if you look at your graph of this function, the graph of this function between pi and 2 pi for this, it actually kind of looks like this. Here's pi, and here's 2 pi. Since it's underneath the curve right here, this area is kind of negative. So when we integrate it, we want our area to always be positive, same way you kind of want distance to be positive. So you're going to get a negative number since it's all underneath the curve. You just take that and you multiply it by negative 1 to really give you a positive area. So we integrate it just the same. Since we've already integrated by parts, don't do the work again. So we're instead of integrating, 8x sine dx between pi and 2 pi, we already did the integration work here, so we just take our antiderivative here, 8x cosine of x plus 8 sine of x, and we evaluate that between pi and 2 pi. And what you should get when you do that is you should get negative, since we're taking the negative of this, you get negative 24 pi, but you don't want a negative area, so we just kind of multiply it by negative 1. So the answer is 24 pi. Here's how you cheat on this. You put this original function into your calculator. Since in trig functions, most of the time you might get in terms of pi. So go ahead and put 8x sine of x into your calculator and do the second calc. So when you put this function into the y1 line of your calculator, and you do that trick where you do second calc, and you choose option 7, integrate f of x dx, it'll shade in the area for you, and it'll give you this really weird looking decimal. It'll give you negative 75.39822, blah, 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 blah. Alright, hit math when you're in that point, and do math enter, because maybe it'll rationalize that into fraction, but we're disappointed to see it doesn't change it into a fraction. But then take that same value, don't approximate it, and just divide it by pi. And if you notice, if you divide, since this is really in terms of pi, but it's a weird decimal, when you divide it by pi, you get negative 24. So that tells you that this thing was really negative 24 pi. So if you have trouble with these, and you know they're in terms of pi, and really on any question, you know the answer's in terms of pi, you can cheat by making your calculator do the answer, divide it by pi, and just make sure to reintroduce that pi term at the end, and you can do a lot of problems like that. Alright, good luck, guys.